Hello there, and welcome to a gentle journey through the cosmos. Tonight, we're going to drift among the stars and explore the universe in the most peaceful way possible. We'll discover fascinating truths about space that feel like whispered secrets, each one more calming than the last. Some will make you smile softly in the darkness. Others will fill you with a quiet sense of wonder that settles deep into your bones. But all of them are designed to carry you gently toward sleep while your mind wanders through the infinite beauty above. If you enjoy these cosmic lullabies, feel free to like this video and subscribe for more peaceful explorations. You can also share your own favorite space facts in the comments below. But for now, just get comfortable. Let your breathing slow, your shoulders relax, and allow the gentle mysteries of the universe to wash over you like starlight. Let's begin our quiet voyage into the night sky. The universe is mostly empty space, and there's something deeply peaceful about that. When you look up at the night sky, you're seeing a vast ocean of nothingness, punctuated by tiny islands of light. Between the stars lies an almost perfect vacuum, stretches of space so empty that you could travel for millions of miles without encountering a single atom. This emptiness isn't lonely or cold in the way we might imagine. Instead, it's serene, like walking through a cathedral where silence itself becomes sacred. The spaces between stars are where light travels unimpeded, where cosmic rays dance freely, and where the universe simply exists in its purest form. Stars are born in the most gentle way imaginable. Far out in space, clouds of gas and dust drift slowly through the darkness like cosmic cotton. These clouds, called nebulae, are so thin you could wave your hand through them and barely disturb a few atoms. But given enough time, gravity works its quiet magic. The cloud begins to pull itself together, not with violence or force, but with the patient persistence of raindrops gathering on a window. As the cloud contracts, it grows warmer, like cupping your hands around a candle flame. Eventually, the center becomes so hot and dense that hydrogen atoms begin to fuse together, and a new star ignites with the soft glow of a cosmic nightlight. The light from distant stars takes years to reach your eyes. When you step outside on a clear night and look up, you're seeing the universe as it was in the past. The light from the nearest star beyond our sun left its surface over 4 years ago. Light from other stars began its journey decades, centuries, or even millennia before you were born. This means that starlight is time travel in its most gentle form. You're literally looking backward through time, seeing ancient light that has been traveling through space for longer than human civilizations have existed. There's something profoundly comforting about this connection across time, knowing that the same starlight that touches your face tonight once illuminated the dreams of people who lived hundreds of years ago. Our galaxy moves through space like a slow cosmic river. The Milky Way is drifting through the universe at about 600 kilometers per second, but this motion is so smooth and steady that we never feel it. We're passengers on a galactic ship, sailing through an ocean of space so vast that our fastest rockets would take tens of thousands of years just to reach the next star. This motion isn't random or chaotic. Our galaxy follows invisible currents in space, pulled gently by the gravity of distant galaxy clusters. We're all traveling together on this cosmic journey, every person, every tree, every grain of sand, moving as one through the endless night. The universe has a natural rhythm that beats slower than your heart. Deep space is filled with pulsars, which are rapidly spinning neutron stars that sweep beams of radio waves across the cosmos like lighthouse beacons. Some pulsars spin so regularly that they keep time more accurately than the most precise atomic clocks on Earth. These cosmic metronomes pulse with mathematical precision, sending their signals across the galaxy with the reliability of waves lapping against a shore. Listening to pulsar signals converted to audio creates a gentle, rhythmic tapping that sounds like rain on a roof or the distant beat of a cosmic drum, providing a steady soundtrack to the universe's quiet symphony. Planets are scattered throughout the galaxy like seeds in a cosmic garden. Astronomers have discovered thousands of worlds orbiting other stars, and each one is unique. Some are scorching hot worlds where the surface glows like molten glass. Others are frozen ice balls where the atmosphere has crystallized into snow. But many exist in that perfect zone around their star where liquid water could exist, where the temperature is just right for life as we know it. These worlds drift silently through space, each one a potential home, each one carrying the possibility of its own quiet story unfolding under alien skies. The cosmic microwave background fills the universe with the gentlest possible glow. This faint radiation is the afterglow of the Big Bang itself, cooled and stretched by billions of years of expansion until it's barely warmer than absolute zero. You can't see it with your eyes, but it's everywhere around you, a soft cosmic embrace that connects every point in space. This ancient light has been traveling for nearly 14 billion years, carrying with it the memory of when the universe first became transparent, and light could travel freely through space. It's like a cosmic lullaby, the universe's own gentle humming that has been playing since the beginning of time. Black holes are not the violent monsters they're often portrayed as. At a safe distance, a black hole is simply a region where gravity is so strong that not even light can escape. But this doesn't mean they're sucking everything into oblivion. In fact, if our sun were replaced by a black hole of the same mass, Earth would continue orbiting exactly as it does now, just in darkness. Black holes are more like cosmic drains, quietly collecting material that ventures too close while leaving the rest of the universe completely undisturbed. They're patient and still, warping space around them in gentle curves that guide matter and energy along invisible paths. Comets are cosmic snowballs that spend most of their time in the quiet suburbs of the solar system. Far beyond the orbit of Pluto lies the Oort cloud, a vast sphere of icy objects that surrounds our solar system like a cosmic snow globe. These ancient remnants from the formation of the planets drift in the cold darkness, taking millions of years to complete a single orbit around the Sun. Occasionally, the gravity of a passing star nudges one of these ice balls toward the inner solar system, where the Sun's warmth begins to sublimate its frozen surface, creating the beautiful tail that makes comets so mesmerizing. But most of the time, they simply sleep in the darkness, waiting patiently for their moment in the sun. The space between galaxies is even more peaceful than the space between stars. Intergalactic space is so empty that the average density is less than 1 atom per cubic meter. If you could somehow travel to these regions, you would find yourself in the most serene environment possible, surrounded by nothing but the faintest whisper of hydrogen gas and the gentle glow of the cosmic microwave background. Here, time moves differently. Without the gravitational influence of nearby stars or planets, a spacecraft could coast for billions of years without encountering anything more substantial than a few stray atoms. It's the ultimate quiet place where the universe exists in its most minimal state. Saturn's rings are made of countless ice particles, each one catching and reflecting sunlight like tiny mirrors. These particles range in size from dust grains to house-sized chunks, all orbiting Saturn in perfect harmony. The rings are incredibly thin, sometimes only a few dozen meters thick, despite stretching for hundreds of thousands of kilometers. They create shadows on Saturn's surface and are themselves shadowed by the planet, creating a complex dance of light and darkness that changes with Saturn's seasons. The rings are not solid, but more like a cosmic ballet, with each particle following its own orbital path, while contributing to the overall pattern that makes Saturn one of the most beautiful sights in the solar system. Jupiter acts as a cosmic guardian for the inner solar system. Its massive gravity field deflects or captures many asteroids and comets that might otherwise threaten Earth. Over billions of years, Jupiter has quietly protected our planet, allowing life to evolve without constant bombardment from space debris. The gas giant's Great Red Spot, a storm that has been raging for centuries, is larger than Earth itself, yet it spins with a stately grace that has captivated observers for generations. Jupiter's many moons create a miniature solar system, each world with its own character, from volcanic Io to ice-covered Europa with its hidden ocean. The sun burns with the steady warmth of 4 billion years of continuous fusion. In its core, hydrogen atoms fuse into helium at a rate of 600 million tons per second, releasing the energy that lights our days and warms our world. This process is so efficient that the sun has enough fuel to continue shining for another 5 billion years. The energy created in the sun's core takes thousands of years to work its way to the surface, bouncing around like a pinball through the dense interior before finally emerging as the sunlight that reaches Earth in just 8 minutes. This means that the warmth you feel on your face today began its journey in the heart of the sun long before human civilization began. The moon drifts away from Earth at the pace of your fingernails growing. Each year, Auriel Companion moves Celeste about 1.5 inches farther from us, a separation so gradual it's almost imperceptible. This slow dance has been going on for billions of years, and it will continue for billions more. Long ago, the moon hung much closer to Earth, appearing enormous in the sky and creating tides that were far more dramatic than today's gentle rise and fall of the oceans. But time has a way of softening even the most intense relationships. The moon's retreat is so gentle that generations of humans have looked up at essentially the same view, finding comfort in its familiar face and phases. Venus rotates backwards compared to most planets, turning slowly in the opposite direction like a cosmic ballerina spinning in reverse. A day on Venus lasts longer than its year, with the planet taking 243 Earth days to complete one rotation, but only 225 days to orbit the Sun. This leisurely backward spin creates the most unusual sunrises and sunsets in the solar system, where the sun appears to rise in the west and set in the east. The rotation is so slow that you could walk faster than the planet turns, staying ahead of the sunset indefinitely if you could somehow stroll across its cloud-covered surface. Neutron stars are the universe's most efficient recyclers. When a massive star dies in a supernova explosion, its core collapses into an object so dense that a teaspoon of its material would weigh as much as a mountain. These stellar remnants are only about 12 miles across, yet they contain more mass than our entire sun. Despite their incredible density, neutron stars rotate with clockwork precision, some spinning hundreds of times per second while maintaining perfect regularity. They're like cosmic lighthouses, sweeping beams of radiation across space with such reliability that astronomers use them as natural clocks to measure the fabric of space-time itself. The Voyager spacecraft are humanity's most distant ambassadors, still sending whispered messages back to Earth after more than 4 decades of travel. These robotic explorers have crossed the boundary of our solar system and now drift through interstellar space, farther from home than any human-made object has ever traveled. Their signals take over 20 hours to reach Earth, growing fainter each year as they journey deeper into the cosmic ocean. Yet they continue to transmit data about their lonely voyage, sharing discoveries about the space between stars with the patience of cosmic monks sending letters from a distant monastery. Mars experiences seasons just like Earth, but each one lasts about twice as long. The red planet tilts on its axis in a similar way to our world, creating familiar patterns of change across its dusty landscape. Martian winters bring carbon dioxide snow to the polar regions, while summer melts the dry ice caps and stirs up planet-wide dust storms that can last for months. These massive storms move with dreamlike slowness, reshaping the surface and creating new patterns in the sand dunes that drift like frozen waves across the ancient terrain. Galaxy clusters drift through space in slow motion, bound together by invisible threads of dark matter. These cosmic cities contain hundreds or thousands of galaxies, each one a collection of billions of stars, all held in a gentle gravitational embrace that has lasted for billions of years. The clusters themselves are connected by vast filaments of matter that stretch across hundreds of millions of light years, creating a cosmic web that gives structure to the entire universe. Between these filaments lie enormous voids, regions so empty that a traveler could journey for hundreds of millions of years without encountering a single galaxy. The solar wind carries the sun's influence far beyond the planets, creating a vast bubble of charged particles that surrounds our entire solar system. This invisible solar atmosphere, called the heliosphere, protects us from some of the harsh radiation that fills interstellar space. The boundary where the solar wind meets the interstellar medium creates a shock wave that ripples outward like the wake of a boat moving through still water. Beyond this boundary lies the true interstellar ocean, where the influence of our sun finally fades and the galaxy's own gentle currents take over. Brown dwarfs are the universe's failed stars, objects too small to sustain nuclear fusion but too large to be called planets. These cosmic in-betweens drift through space in a state of perpetual twilight, glowing dimly with leftover heat from their formation billions of years ago. They're like stellar embers, slowly cooling over time but never quite going dark. Some brown dwarfs have their own planetary systems, creating miniature solar systems where worlds orbit around these dim, reddish stars that barely illuminate their surfaces with the faint glow of dying coals. The cosmic web reveals itself in the largest structures in the universe. When astronomers map the positions of millions of galaxies, they discover that matter isn't distributed randomly through space, but follows intricate patterns that look remarkably like neural networks or soap bubble foam. Galaxies cluster along filaments separated by vast, empty regions, creating a three-dimensional tapestry that spans the observable universe. This cosmic architecture formed over billions of years as gravity slowly sculpted the initial tiny fluctuations in density that emerged from the Big Bang into the majestic structures we see today. Tidal forces create some of the most gentle phenomena in the cosmos. The same gravitational pull that raises Earth's oceans also shapes the rings of Saturn, keeps one face of the moon always pointed toward Earth, and creates the beautiful spiral arms of galaxies. These forces work slowly and patiently, like an artist working with clay over geological timescales. On Jupiter's moon Europa, tidal heating from the giant planet's gravity keeps an ocean of liquid water warm beneath miles of ice, creating one of the most promising places to search for life beyond Earth. The Milky Way's central black hole rests quietly at the heart of our galaxy like a sleeping giant. Despite containing the mass of 4 million suns, Sagittarius A star rarely shows signs of activity, occasionally flickering as small amounts of matter fall past its event horizon. Most of the time, it simply sits in the darkness, its presence revealed only by the elegant dance of nearby stars that orbit it in precisely choreographed ellipses. These stellar orbits provide a cosmic clock, marking time on scales that dwarf human history while demonstrating the patient persistence of gravity across millions of years. Asteroid belts are far more spacious than science fiction suggests. The asteroid belt between Mars and Jupiter contains millions of rocky objects, yet they're so spread out that spacecraft regularly pass through without coming close to a single one. If you could stand on one asteroid, the next nearest one would likely appear as nothing more than a dim point of light, indistinguishable from the stars. These ancient remnants from the solar system's formation drift in their orbits like a sparse collection of cosmic pebbles scattered across a vast desert, each one following its own path around the sun with mathematical precision. The universe's expansion means that distant galaxies are moving away from us not through space, but with space itself. This cosmic stretching happens so gradually that it's imperceptible on human scales, yet over billions of years, it will carry the most distant galaxies beyond our ability to see them. Eventually, far in the future, observers in our galaxy will look out into a universe that appears much emptier than the one we see today. The expansion creates a kind of cosmic horizon beyond which information can never reach us, making the universe both infinite in scope and intimate in its accessibility. Binary stars waltz through space in gravitational partnerships that can last for billions of years. These stellar couples orbit around their common center of mass with the grace of cosmic dancers. Some so close they share material between them, while others maintain a respectful distance measured in light hours or light days. About half of all stars exist in these binary relationships, creating systems where two suns rise and set in alien skies, casting double shadows and painting landscapes in the combined light of their different colored stars. Meteor showers are the universe's way of celebrating in the quietest possible manner. These cosmic light shows happen when Earth passes through the debris trail left behind by a comet, and tiny particles no larger than grains of sand burn up in our atmosphere, creating streaks of light that last for just a few seconds. The meteors appear to radiate from a single point in the sky, like gentle fireworks spreading outward in slow motion. Most meteor showers are so predictable that astronomers can tell you exactly when they'll peak, sometimes decades in advance. These celestial events remind us that we're constantly moving through space, sweeping up the ancient dust of comets that passed our way, long before humans ever looked up at the stars. The speed of light creates a natural speed limit that makes the universe feel more manageable. Nothing can travel faster than light, which means that even the most energetic cosmic events unfold with a certain stately pace. When a star explodes in a distant galaxy, the light from that explosion travels toward us at 186,000 miles per second, yet it still takes millions or billions of years to arrive. This cosmic speed limit ensures that change happens gradually on astronomical scales, giving the universe a sense of stability and permanence that's deeply comforting. It means that the night sky we see tonight will look essentially the same tomorrow night, and for countless nights to come. Galaxies come in beautiful spiral shapes because of density waves that move through them like ripples on a cosmic pond. These waves don't carry matter along with them, but instead create regions where stars form more frequently, lighting up the spiral arms with the blue glow of young, hot stars. The waves themselves move more slowly than the stars, so individual stars drift in and out of the spiral arms over millions of years, like cars moving through a traffic jam that maintains its pattern even as the vehicles change. This process has been shaping our galaxy for billions of years, creating the elegant pinwheel structure that would be visible to observers in distant galaxies looking back at us. Red dwarf stars are the universe's most patient residents. These small, cool stars burn their hydrogen fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. Most of the stars in our galaxy are red dwarfs, quietly glowing with a dim, reddish light that could outlast every other type of star. They're like cosmic candles that never burn out, providing steady, if faint, illumination to any planets that might orbit them. In the far future, when all the massive stars have burned out and even the sun has faded to a white dwarf, red dwarf stars will still be shining, the last lights in an aging universe. Space-time itself ripples when massive objects accelerate, creating gravitational waves that spread outward at the speed of light like waves on an invisible ocean. These ripples are so subtle that they stretch and compress space by less than the width of a proton, yet sensitive detectors on Earth can now measure them when black holes collide billions of light years away. The waves carry information about some of the most violent events in the universe, yet by the time they reach us, they're as gentle as the faintest whisper, barely disturbing the fabric of reality as they pass through our planet and continue on their eternal journey through space. Exoplanets orbit other stars in an amazing variety of configurations that challenge our understanding of how planetary systems form. Some planets orbit so close to their stars that their surfaces are molten rock, while others drift so far away that any atmosphered. There are planets that orbit binary would freeze Soli stars, experiencing double sunrises and sunsets, and planets that have been flung out of their systems entirely, wandering alone through interstellar space like cosmic nomads. Each of these worlds represents a different experiment in planetary formation, a unique solution to the gravitational puzzle of how matter organizes itself around a star. The solar system has a rhythm that governs the dance of planets, with orbital periods that create beautiful mathematical relationships. Jupiter completes one orbit around the Sun in the time it takes Earth to orbit nearly 12 times, while Saturn takes about 30 Earth years to complete its stately circuit. These orbital relationships create a kind of cosmic music, with gravitational influences that strengthen and weaken in predictable cycles. The planets never return to exactly the same configuration twice, yet their movements follow patterns that have persisted for billions of years, creating a celestial clockwork that keeps perfect time on scales beyond human comprehension. Magnetic fields throughout the universe create invisible sculptures in space, guiding the flow of charged particles along elegant curves and spirals. Earth's magnetic field protects us from the solar wind, deflecting charged particles toward the poles where they create the shimmering curtains of the aurora. Jupiter's magnetic field is so powerful that it traps particles from its volcanic moon, Io, creating radiation belts that would be dangerous to spacecraft. Even galaxies have magnetic fields that help shape the formation of stars and guide cosmic rays on their journeys between the stars, creating an invisible architecture that influences the structure of the universe itself. White dwarf stars are the peaceful retirement homes of sun-like stars. When a star like our Sun exhausts its nuclear fuel, it gently sheds its outer layers and settles down into a white dwarf, a hot, dense object about the size of Earth but containing most of the original star's mass. These stellar remnants cool slowly over billions of years, fading from white to yellow to red, and eventually to black, though the universe isn't old enough yet for any white dwarf to have completed this journey. They represent the quiet end of stellar life, not with the violence of a supernova, but with the gentle dignity of a star that has given its light to the universe for billions of years and now rests in cosmic peace. The cosmic microwave background carries tiny temperature variations that reveal the seeds of all large-scale structure in the universe. These minute fluctuations, differing by only millionths of a degree, mark the regions where matter was slightly denser in the early universe. Over billions of years, gravity amplified these tiny differences until they became the galaxies, galaxy clusters, and vast voids we see today. The pattern of these fluctuations follows the predictions of cosmic inflation theory, suggesting that the entire observable universe once existed in a region smaller than a proton before expanding faster than light in the first fraction of a second after the Big Bang. Solar eclipses create one of the most serene spectacles in nature when the moon passes directly between Earth and the sun, casting a shadow that races across our planet at thousands of miles per hour. In the path of totality, day turns to night in a matter of minutes. Stars become visible in the darkened sky, and the sun's corona emerges as a ghostly crown of light around the silhouetted moon. The temperature drops, animals grow quiet, and for a few precious minutes, observers experience a connection to the cosmic clockwork that governs our solar system. These alignments are so precise that astronomers can predict eclipses centuries in advance. Yet each one feels miraculous to enough to witness it. Voy, those Lucky-Ager's golden records carry the sounds of Earth into the cosmic ocean, including recordings of wind, rain, surf, birds, whales, and human music from around the world. These time capsules also contain greetings in 55 languages and images that tell the story of our planet and its inhabitants. The records are made of gold-plated copper designed to last for billions of years in the vacuum of space, long after the civilizations that created them have been forgotten. They drift now through interstellar space, humanity's message to the cosmos, carrying our voices and music to places we may never reach, a gentle introduction to whoever might find them in the distant future. The heliopause marks the boundary where the solar wind meets the interstellar medium, creating a vast bubble around our solar system that astronomers call the heliosphere. This invisible barrier, located about 100 times farther from the Sun than Earth, represents the edge of our Sun's direct influence and the beginning of true interstellar space. The Voyager spacecraft crossed this boundary and discovered that the space beyond is filled with cosmic rays and particles from other stars, a galactic environment that our sun's magnetic field had been protecting us from. It's like stepping from a sheltered harbor into the open ocean, leaving the familiar for the vast unknown. Planetary rings exist throughout the solar system, not just around Saturn. Jupiter has faint rings made of dust from its innermost moons, while Uranus and Neptune each have their own ring systems, though much darker and more difficult to observe. These rings form when moons venture too close to their parent planet and are torn apart by tidal forces, or when asteroids or comets crash into existing moons, creating debris that settles into orbit. The particles in these rings range from tiny dust grains to house-sized boulders, all following their own orbital paths while contributing to the overall structure that makes each ring system unique. The universe's large-scale structure resembles a cosmic web, with galaxies strung along filaments separated by enormous voids that contain almost nothing. These voids, some hundreds of millions of light years across, are the most empty places in the universe, containing so few galaxies that a traveler could journey for eons without encountering a single star. Between the filaments and voids, matter flows in slow currents guided by gravity, creating a pattern that emerged from tiny quantum fluctuations in the first moments after the Big Bang and has been growing ever since under the patient influence of dark matter and dark energy. The Milky Way will eventually merge with the Andromeda Galaxy in a cosmic collision that will unfold over billions of years. Despite the dramatic name, this galactic merger will be surprisingly gentle, as the vast distances between individual stars mean that actual collisions between stars will be extremely rare. Instead, the two galaxies will dance around each other, their spiral arms disrupted and reformed, until they settle into a new elliptical galaxy that astronomers have already nicknamed Milkomeda. This cosmic choreography will play out so slowly that hundreds of billions of generations could pass before the merger is complete, making it more like a stately waltz than a violent crash. Pulsars serve as cosmic lighthouses, sweeping beams of radiation across space with such regularity that they can be used as natural clocks, more precise than any timepiece on Earth. These rapidly spinning neutron stars, some rotating hundreds of times per second, maintain their rhythm with such consistency that astronomers use them to test Einstein's theories and search for gravitational waves. The most stable pulsars keep time so accurately that they gain or lose less than a second over millions of years, creating a network of natural chronometers scattered throughout the galaxy that tick away the eons with mechanical precision. The cosmic distance ladder allows astronomers to measure vast distances by using a series of overlapping techniques, each one extending our reach deeper into space. Starting with parallax measurements to nearby stars, astronomers can calibrate the brightness of variable stars, which can then be used to measure distances to nearby galaxies, which in turn help calibrate even more distant markers like supernova. Each rung of this ladder depends on the accuracy of the previous one, creating a chain of measurements that extends our vision across billions of light years to the edge of the observable universe, like a cosmic measuring tape stretching across the void. The aurora dances across polar skies like nature's own gentle light show, created when charged particles from the solar wind interact with Earth's magnetic field. These ethereal curtains of green, blue, and sometimes red light shimmer and flow with an otherworldly grace, appearing to move in slow motion across the star-filled darkness. the lights follow the invisible lines of Earth's magnetic field, creating arcs and spirals that can stretch for hundreds of miles across the sky. Indigenous peoples have watched these lights for thousands of years, creating beautiful stories to explain their presence, from dancing spirits to bridges between worlds. The aurora occurs most frequently during periods of high solar activity, yet even during quiet times, the lights continue their patient dance, visible to anyone willing to venture into the cold darkness of polar nights. Planetary migration shaped our solar system in ways we're only beginning to understand. The giant planets didn't form where we find them today, but instead wandered inward and outward over millions of years, pushed and pulled by gravitational interactions with the disk of gas and dust that surrounded the young sun. Jupiter may have migrated all the way to Mars's current orbit before reversing course and moving back outward, clearing the inner solar system of debris and allowing the rocky planets to form. This grand tack model explains many puzzles about our solar system's architecture, from the asteroid belt's sparse population to the precise spacing of the planets. The migration happened so gradually that it took millions of years to complete, like a cosmic game of musical chairs played out over geological time. Cosmic rays travel across the galaxy for millions of years before reaching Earth, carrying with them the signatures of distant supernovae and other high-energy events. These subatomic particles, mostly protons moving at nearly the speed of light, bounce off magnetic fields throughout the galaxy like pinballs in a cosmic arcade machine. Their journeys are so long and complex that by the time they reach Earth, we can no longer determine where they originated. Some cosmic rays may have begun their voyage before our solar system even formed, wandering the galaxy like ancient messengers carrying news of long-dead stars. When they finally encounter Earth's atmosphere, they create cascades of secondary particles that rain down gently on the surface, invisible reminders of the high-energy universe that surrounds us. Stellar nurseries are regions where new stars form with the patience of cosmic gardeners. These nebulae, often illuminated by the light of young, hot stars, can stretch for hundreds of light years and contain enough material to form thousands of new suns. The process begins when shock waves from nearby supernovae or the gravitational influence of passing stars compresses the gas and dust, causing it to collapse under its own weight. Within these collapsing regions, dense knots form that will eventually become individual stars, each one taking millions of years to gather enough material and reach the temperatures needed for nuclear fusion. The youngest stars often remain hidden within their dusty cocoons for millions of years before emerging as fully formed members of the galactic community. The interstellar medium fills the space between stars with an incredibly thin soup of gas and dust that plays a crucial role in galactic ecology. This tenuous material, averaging less than 1 atom per cubic centimeter, serves as the raw material for future generations of stars while also carrying away the enriched gas expelled by dying stars. Vast bubbles and stellar winds and supernova explosions create this medium, carving out regions of hot, rarefied gas that can persist for millions of years. These superbubbles can merge and interact with each other, creating a complex, ever-changing structure that shapes the flow of matter throughout the galaxy. Despite its incredibly low density, the interstellar medium contains enough material to form billions of new stars over the galaxy's lifetime. Trojan asteroids share orbital paths with planets, following the same route around the Sun but staying a safe distance away like cosmic hitchhikers. These objects cluster at gravitationally stable points called Lagrange points, located about 60 degrees ahead of and behind the planet in its orbit. Jupiter has the largest collection of Trojan asteroids, with thousands of these rocky bodies sharing the giant planet's path around the Sun. The gravitational balance at these points is so delicate that the asteroids can remain there for billions of years, gently oscillating around the Lagrange points like marbles rolling around the bottom of a shallow bowl. Even Earth has a few Trojan companions, small asteroids that follow our planet's orbit while maintaining their respectful distance. The galactic halo surrounds our galaxy like an invisible sphere, containing ancient star clusters called globular clusters that orbit the Milky Way's center in highly elliptical paths. These stellar cities contain some of the oldest stars in the galaxy, formed when the universe was young and contained much less of the heavy elements that make planets and life possible. The globular clusters swing through the galactic disk like cosmic comets, taking hundreds of millions of years to complete their orbits. During their passages through the disk, they can gravitationally stir up the stars and gas they encounter. Yet they remain remarkably stable structures, held together by their own gravity for billions of years. Some globular clusters contain hundreds of thousands of stars packed into a region on only a few dozen light years across. Planetary atmospheres create their own weather patterns that can persist for centuries or change rapidly over the course of days. Venus's thick atmosphere rotates faster than the planet itself, creating super-rotating winds that circle the globe in just 4 Earth days. Mars experiences planet-wide dust storms that can last for months, while Jupiter's Great Red Spot has been a stable weather feature for at least 300 years. These atmospheric phenomena demonstrate how different conditions can lead to radically different climates, from Venus's crushing greenhouse effect to Mars's thin atmosphere that can barely support liquid water. Each planet's atmosphere tells a story about its formation, evolution, and interaction with the solar wind over billions of years. Magnetospheres protect planets from the harsh environment of space by deflecting charged particles from the solar wind. Earth's magnetic field creates a teardrop-shaped bubble around our planet that extends far beyond the orbit of the Moon on the side facing away from the Sun. This invisible shield channels dangerous radiation toward the poles, where it creates the beautiful aurora while protecting the delicate atmosphere from being stripped away by the solar wind. Not all planets are so fortunate. Mars lost most of its magnetic field billions of years ago, allowing its atmosphere to slowly leak into space. The interaction between magnetic fields and the solar wind creates a complex, dynamic system that responds to changes in solar activity with the fluid grace of an invisible cosmic weather system. Rogue planets wander through interstellar space without a star to call home, ejected from their birth systems by gravitational interactions with other planets or passing stars. These cosmic nomads drift through the galaxy in darkness, their surfaces frozen and lifeless, unless they retain enough internal heat from their formation to maintain subsurface oceans. Some estimates suggest there may be more rogue planets than stars in our galaxy, a vast population of worlds that follow their own paths through space without the guiding influence of stellar gravity. These planetary wanderers represent a different kind of cosmic loneliness, worlds that have lost their connection to the warmth and light of a star, yet continue their journey through the galaxy with patient determination. The cosmic web's filaments stretch across hundreds of millions of light years, creating the largest structures in the known universe. These vast threads of dark matter and galaxies form at the intersections of even larger structures, creating nodes where galaxy clusters gather like cosmic cities at the crossroads of invisible highways. The filaments themselves are mostly empty space with galaxies strung along them like pearls on cosmic necklaces, separated by distances so vast that light from one galaxy group takes millions of years to reach the next. Between the filaments lie the cosmic voids, regions so empty that they contain less than 1/10 the average density of matter in the universe, creating a cosmic landscape that resembles a three-dimensional spider web spanning the entire observable cosmos. Stellar evolution follows predictable patterns that depend on a star's initial mass, like a cosmic recipe that determines the entire life cycle from birth to death. The most massive stars live fast and die young, burning through their nuclear fuel in just millions of years before exploding as supernovae. Medium-sized stars like our Sun live for billions of years, slowly converting hydrogen to helium in their cores before gently shedding their outer layers to become white dwarfs. The smallest red dwarf stars are so efficient with their fuel that they can shine for trillions of years, outlasting every other type of star and potentially providing stable energy sources for planetary systems long after larger stars have burned out. This cosmic hierarchy ensures that the galaxy will continue to have active stars for far longer than the current age of the universe. Tidal heating occurs when gravitational forces stretch and compress celestial bodies, generating internal heat through friction. Jupiter's moon, Io, experiences such intense tidal heating that it has become the most volcanically active body in the solar system, with sulfur eruptions that can shoot hundreds of miles above its surface. Europa's subsurface ocean remains liquid despite being far from the sun, because Jupiter's gravity kneads the moon's interior like cosmic bread dough, generating enough heat to prevent the ocean from freezing. This process works on many scales throughout the universe, from keeping small moons geologically active to helping maintain the spiral structure of galaxies through gravitational interactions between neighboring star systems. Binary black holes create some of the most energetic events in the universe when they finally merge after spiraling around each other for millions of years. As these cosmic monsters draw closer together, they warp space-time so severely that they generate gravitational waves detectable across billions of light years. The final moments of their dance happen incredibly quickly, with the black holes completing dozens of orbits per second before merging in a cataclysmic event that releases more energy in gravitational waves than all the stars in the observable universe emit in light. Yet even these violent cosmic collisions unfold with a kind of inevitability, following the mathematical precision of Einstein's equations as they reshape the fabric of reality itself. The galactic center harbors mysteries that we're only beginning to understand, including a supermassive black hole surrounded by a cluster of massive stars that orbit it in precisely calculated ellipses. These stars, some of the most massive known, complete their orbits in periods ranging from decades to centuries, providing a natural laboratory for testing general relativity in the strongest gravitational field, accessible to direct observation. The region also contains vast molecular clouds, stellar nurseries, and remnants of ancient star formation episodes that paint a complex picture of galactic evolution. Radio telescopes can peer through the dust that obscures our view of the galactic center, revealing a dynamic environment where matter and energy flow in patterns shaped by the center, black hole's immense gravity. Planetary rings evolve over time through collisions, gravitational interactions, and the slow migration of ring particles toward or away from their parent planet. Saturn's rings may be much younger than previously thought, possibly forming from the destruction of a large moon within the past few 100 million years. The intricate structure within the rings, including gaps, spokes, and shepherd moons, demonstrates how gravitational forces can create order from chaos on cosmic scales. Some ring particles clump together temporarily before being torn apart again, creating transient features that come and go like waves on a cosmic beach. The rings serve as natural laboratories for studying how disk-like structures form and evolve, providing insights into everything from planetary formation to the structure of spiral galaxies. Space weather affects technology throughout the solar system, from satellites in Earth orbit to spacecraft exploring the outer planets. Solar flares and coronal mass ejections send streams of charged particles racing through space at millions of miles per hour, creating disturbances in planetary magnetospheres that can disrupt communications and navigation systems. These space storms follow an 11-year cycle linked to the Sun's magnetic field, which flips polarity regularly in a process that's still not fully understood. During solar maximum, the increased activity creates more frequent auroras on Earth and other planets with magnetic fields, while also posing greater risks to astronauts and sensitive electronic equipment. The Sun's influence extends far beyond the visible light and heat we experience, creating an invisible weather system that affects the entire solar system. Cosmic evolution proceeds on timescales so vast that entire civilizations could rise and fall in what amounts to cosmic moments. The universe has been expanding and cooling for nearly 14 billion years, allowing the first stars to form, live their lives, and enrich space with the heavy elements necessary for planets and life. Galaxies have had time to form, merge, and evolve into the structures we see today, while the cosmic web has grown from tiny quantum fluctuations into the largest patterns in the universe. Yet on cosmic scales, we live in a young universe where most of the stars that will ever exist have yet to be born, and the expansion will continue for trillions of years to come, carrying galaxies ever farther apart until the cosmos becomes a much lonelier place than it is today. The heliosheath represents the final frontier of our solar system's influence, a turbulent region where the solar wind slows down and mingles with the interstellar medium. This boundary layer extends for billions of miles around the solar system, creating a vast transition zone between the Sun's domain and the broader Voyager spacecraft discovered galactic environment. Said that this region is filled with energetic particles and magnetic field lines that twist and reconnect in complex patterns, creating a dynamic interface between two very different plasma environments. Beyond the heliosheath lies the true interstellar medium, where our sun's influence finally fades and gives way to the collective effects of all the other stars in the galaxy, marking humanity's first tentative steps into the cosmic ocean that surrounds us. The cosmic dance of stellar formation reveals itself in the most unexpected places throughout the universe. Deep within the Eagle Nebula, towering pillars of gas and dust stretch across light years, sculpted by the gentle pressure of starlight from nearby young stars. These cosmic sculptures, sometimes called the pillars of creation, demonstrate how light itself can be a force of change, slowly eroding the dense clouds while simultaneously triggering the birth of new stars within their depths. The process unfolds with the patience of geological time, each pillar taking millions of years to evolve and change shape. Within these structures, gravity works quietly to pull material together into dense knots that will eventually ignite as new suns, continuing the endless cycle of stellar birth and death that has shaped our galaxy for billions of years. Dark matter weaves invisible threads throughout the cosmos, creating a hidden architecture that guides the formation of everything we can see. This mysterious substance, which makes up about 5 times more mass than ordinary matter, reveals itself only through its gravitational effects on visible galaxies and stars. Computer simulations show how dark matter forms vast halos around galaxies, providing the gravitational scaffolding that allows normal matter to settle into the spiral arms and stellar disks we observe. These dark matter structures grew from tiny density fluctuations in the early universe, slowly accumulating over billions of years into the cosmic web that underlies all large-scale structure. Without this invisible foundation, galaxies as we know them could never have formed, making dark matter one of the universe's most important yet mysterious components. Galactic fountains cycle matter between the disk and halo of spiral galaxies in a process that resembles a cosmic water feature. Hot gas heated by stellar winds and supernovae rises from the galactic disk like steam, cooling as it travels hundreds of thousands of light years above the plane of the galaxy, before eventually falling back down as a gentle rain of material that can fuel new star formation. This galactic circulation system operates on timescales of hundreds of millions of years, slowly mixing the chemical elements produced by different generations of stars throughout the galaxy's volume. The process helps explain how heavy elements created in stellar cores eventually find their way into new star-forming regions, ensuring that each generation of stars contains slightly more of the building blocks necessary for planets and life. Gravitational lensing allows us to peer deeper into the universe by using massive galaxy clusters as natural telescopes. When light from distant galaxies passes through the intense gravitational field of a foreground cluster, space itself bends the light rays like a cosmic magnifying glass, creating multiple images of the background galaxy that are brightened and distorted in beautiful arcs and rings. This effect, predicted by Einstein's general relativity, enables astronomers to observe galaxies so distant that their light began its journey when the universe was less than 1 billion years old. The lensing reveals not only the distant galaxies themselves, but also the distribution of dark matter in the foreground cluster, creating detailed maps of both visible and invisible matter across cosmic distances. These natural telescopes have opened windows into the early universe that would be impossible to achieve with conventional instruments alone. Stellar nurseries operate like cosmic recycling centers, taking the enriched material expelled by previous generations of stars and incorporating it into new stellar systems. When massive stars explode as supernovae, they scatter heavy elements like carbon, oxygen, and iron across vast regions of space, enriching the interstellar medium with the chemical ingredients necessary for rocky planets and organic chemistry. These elements become incorporated into new molecular clouds, where they help cool the gas and allow it to collapse more efficiently into new stars and planetary systems. Each cycle of stellar birth and death increases the metallicity of the galaxy, gradually transforming it from a collection of hydrogen and helium into a complex ecosystem capable of supporting the chemistry of life. This cosmic recycling has been operating for over 10 billion years, slowly building up the chemical complexity we see in the universe today. Planetary systems around other stars display an incredible diversity that challenges our understanding of how worlds form and evolve. Hot Jupiters orbit so close to their stars that their atmospheres are being stripped away, creating comet-like tails of escaping gas super-Earths, larger than our planet but smaller than Neptune, represent a class of world that doesn't exist in our solar system but appears to be common throughout the galaxy. Some exoplanets orbit in the habitable zones of binary star systems, experiencing complex seasons as they receive varying amounts of light from their two suns. Others have been discovered with highly elliptical orbits that carry them from scorching heat to frozen cold during each orbital cycle. This diversity suggests that planetary formation is a remarkably flexible process, capable of creating worlds under conditions that would seem impossible in our own solar system. The cosmic microwave background radiation provides a snapshot of the universe when it was only 380,000 years old, revealing the tiny temperature fluctuations that would eventually grow into the galaxies and galaxy clusters we see today. This ancient light has been stretched by the expansion of the universe from visible wavelengths to microwave frequencies, creating a nearly uniform glow that fills all of space with a temperature just 2.7 degrees above absolute zero. The minute variations in this temperature, differing by only millionths of a degree, correspond to regions where matter was slightly denser or less dense in the early universe. These fluctuations provide crucial evidence for cosmic inflation theory and allow cosmologists to determine fundamental properties of the universe, including its age, composition, and ultimate fate. The cosmic microwave background serves as both a baby picture of the cosmos and a Rosetta Stone for understanding its deepest mysteries. Stellar winds from massive stars shape the interstellar medium like cosmic weather systems, creating vast bubbles and cavities in the gas and dust between stars. These stellar gales can reach speeds of thousands of kilometers per second, carrying away significant fractions of a star's mass over its lifetime while enriching the surrounding space with heavy elements forged in stellar cores. Wolf-Rayet stars, among the most massive and luminous stars known, lose mass so rapidly through their intense winds that they can shed the equivalent of Earth's mass every few thousand years. These powerful outflows interact with surrounding material to create beautiful nebulae and can trigger star formation in nearby molecular clouds by compressing the gas and dust. The collective effect of stellar winds from an entire generation of massive stars can create superbubbles that persist for millions of years, fundamentally altering the structure of the galactic disk. Tidal streams mark the paths of disrupted dwarf galaxies and star clusters as they orbit the Milky Way, creating faint rivers of stars that stretch across the sky like celestial contrails. These stellar streams form when smaller, gravitationally bound systems pass too close to our galaxy's center, causing their outer stars to be stripped away by tidal forces and spread along their orbital path. The Sagittarius stream wraps around our galaxy multiple times, representing the ongoing destruction of a small galaxy that has been orbiting the Milky Way for billions of years. By studying these streams, astronomers can map the gravitational field of our galaxy and learn about the distribution of dark matter that shapes their paths. The streams also provide insights into the hierarchical formation of galaxies, demonstrating how larger systems grow by accreting smaller ones over cosmic time. Cosmic strings, if they exist, would be among the most exotic objects in the universe, representing cracks in the fabric of space-time itself, left over from the earliest moments after the Big Bang. These hypothetical structures would be thinner than a proton but could stretch across the entire observable universe, containing enormous amounts of energy in an incredibly compact form. Cosmic strings would create distinctive signatures in the cosmic microwave background and could generate gravitational waves as they oscillate and interact with each cosmic strings have been definite other. While noisily detected, their possible existence represents a fascinating intersection between particle physics and cosmology, suggesting that the universe may contain relics from phase transitions that occur when it was less than a trillionth of a second old. The search for cosmic strings continues to push the boundaries of observational physics. Polational astronomy and theoreticals or timing arrays use networks of precisely timed neutron stars as cosmic clocks to detect gravitational waves with wavelengths measured in light years. These natural timepieces are so stable that they can reveal the tiny changes in space-time caused by gravitational waves from supermassive black hole mergers in distant galaxies. By monitoring dozens of pulsars simultaneously over many years, astronomers create a galaxy-sized gravitational wave detector that complements the smaller ground-based instruments like LIGO and VIRGO. The technique requires extraordinary precision, measuring arrival times of pulsar pulses to within microseconds over observations spanning decades. Recent results suggest that these arrays may have detected the first evidence of a gravitational wave background, a cosmic hum created by countless black hole mergers throughout the universe's history. Circumstellar disks around young stars provide the raw material for planetary formation, while also serving as natural laboratories for studying how worlds are born. These disks of gas and dust can extend for hundreds of astronomical units from their central star, gradually cooling with distance to create distinct regions where different types of materials can condense. Water ice forms beyond the snowline while rocky materials dominate the inner regions, naturally segregating the building blocks for terrestrial and gas giant planets. Gaps and rings within these disks often indicate the presence of forming planets that are gravitationally clearing their orbital paths, providing direct evidence of planetary formation in action. The study of circumstellar disks has revealed that planet formation begins early and proceeds rapidly, with some systems showing signs of planetary embryos within just a few million years of stellar birth. The local group of galaxies represents our cosmic neighborhood, a collection of about 80 galaxies bound together by gravity and slowly falling toward a larger structure called the Virgo cluster. Our Milky Way and the Andromeda Galaxy dominate this group, with dozens of smaller dwarf galaxies orbiting around them like satellites around planets. The gravitational interactions within the local group create a complex dance of attractions and repulsions that will ultimately lead to the merger of the two largest galaxies in about 4 billion years. Meanwhile, the entire local group is being pulled toward an even larger structure called the Great Attractor, demonstrating how gravity operates on increasingly vast scales to organize matter in the universe. This hierarchical clustering represents one of the fundamental features of cosmic structure, with small groups merging to form larger clusters in an ongoing process of gravitational assembly. Coronal mass ejections represent some of the most dramatic space weather events, hurling billions of tons of charged particles from the sun's outer atmosphere into interplanetary space at speeds exceeding 1 million miles per hour. These magnetic storms can disrupt satellite communications, damage power grids, and create spectacular auroral displays when they interact with Earth's magnetosphere. The sun's corona, normally visible only during solar eclipses, occasionally erupts in these massive outbursts that can affect the entire solar system. Mars, lacking a strong magnetic field, receives the full brunt of these solar storms, which may have contributed to the loss of its atmosphere over billions of years. Understanding coronal mass ejections is crucial for protecting both human technology and future astronauts as we venture deeper into the solar system. Herbig-Haro objects mark the birthplaces of stars with spectacular jets of glowing gas that can extend for light years into space. These cosmic fountains form when material falling onto a young star is redirected along magnetic field lines and expelled in narrow beams at hundreds of kilometers per second. As these jets collide with surrounding gas and dust, they create shock waves that heat the material until it glows with the light of hydrogen, oxygen, and other elements. The jets often show intricate knots and bow shocks that reveal the complex interplay between magnetic fields, gravity, and gas dynamics during star formation. These objects provide crucial insights into how stars regulate their own formation, ejecting excess material and angular momentum to achieve stable nuclear burning. In their cores, galactic archaeology uses the chemical compositions and motions of individual stars to reconstruct the formation history of the Milky Way, treating each star as a fossil record of the conditions when and where it formed. Different stellar populations carry distinctive chemical signatures that reveal their origins in various components of the galaxy, from the ancient halo to the more recently formed disk and bulge. By studying thousands of stars with precise spectroscopy, astronomers can identify streams of stars that originated in disrupted dwarf galaxies, map the chemical evolution of different galactic regions, and even detect evidence of ancient merger events that helped shape our galaxy's structure. This approach has revealed that the Milky Way's formation was far more violent and complex than previously thought, involving multiple episodes of accretion and disruption over billions of years. Magneto-rotational instability drives accretion in disks around black holes and young stars, solving a long-standing puzzle about how material can lose angular momentum and spiral inward. This process occurs when magnetic fields threading through a rotating disk become unstable, creating turbulence that transports angular momentum outward while allowing matter to flow inward. The resulting accretion releases enormous amounts of gravitational potential energy, powering some of the most luminous objects in the universe, including quasars and active galactic nuclei. In circumstellar disks, magneto-rotational instability helps drive the accretion of material onto forming stars, while also contributing to the launching of jets and outflows. Understanding this mechanism has been crucial for explaining how both stars and supermassive black holes can grow by accreting material from their surroundings. Fast radio bursts continue to puzzle astronomers with their brief but incredibly energetic signals that appear to come from random directions across the sky. These millisecond-long pulses release as much energy as the sun produces in several days, yet their sources remain largely mysterious despite the detection of hundreds of examples. Some fast radio bursts repeat, suggesting they come from persistent sources like highly magnetized neutron stars, while others appear only once, possibly indicating catastrophic events like neutron star collisions or the collapse of exotic objects. The signals are dispersed by free electrons in intergalactic space, making them valuable probes of the matter distribution between galaxies. Recent discoveries have begun to associate some fast radio bursts with specific host galaxies, providing crucial clues about their origins and the extreme physics that produces them. Cosmic void surveys reveal that the largest empty regions in the universe are not actually empty, but contain sparse networks of faint galaxies and dark matter filaments. These cosmic deserts, some spanning hundreds of millions of light years, challenge our understanding of structure formation by existing as vast, underdense regions in what should be a relatively uniform universe. The galaxies that do exist in voids often show unusual properties, including higher rates of star formation and different morphologies compared to their counterparts in denser environments. Studying voids provides insights into how gravitational instability operates on the largest scales and helps constrain theories of dark energy and modified gravity. The existence of such large empty regions also raises questions about whether the universe is truly homogeneous on the largest scales or contains structure that extends beyond what current theories predict. Circumgalactic medium surrounds galaxies with vast halos of hot, diffuse gas that can extend for hundreds of thousands of light years beyond the visible stellar disk. This tenuous material, heated to millions of degrees by stellar winds and supernova explosions, represents a significant reservoir of baryonic matter that connects galaxies to the cosmic web of dark matter filaments. The circumgalactic medium serves as both a fuel source for continued star formation and a repository for heavy elements produced by stellar nucleosynthesis, creating a complex ecosystem that regulates galactic evolution. Observations of this material require sophisticated techniques, including absorption line spectroscopy using background quasars as light sources to probe the gas along different sight lines. Understanding the circumgalactic medium is crucial for explaining how galaxies acquire their gas, how they expel material through feedback processes, and how they interact with their cosmic environment. Brown dwarf companions to stars represent a bridge between stellar and planetary formation processes, occupying the mass range where nuclear fusion becomes marginal or impossible. These substellar objects, sometimes called failed stars, can form through gravitational collapse like stars, but lack sufficient mass to sustain hydrogen burning in their cores. Many brown dwarfs exist in binary systems with normal stars, suggesting they form through similar processes, but happen to accrete less material during their formation. Their atmospheres contain complex chemistry, including water vapor, methane, and even clouds of silicate particles, making them natural laboratories for studying atmospheric physics under conditions intermediate between stars and gas giant planets. The discovery of brown, dwarf binaries, and brown dwarfs with planetary companions has expanded our understanding of the continuum between stellar and planetary formation. Gravitational wave astronomy has opened an entirely new window on the universe, allowing us to detect and study events that are invisible to traditional telescopes. The recent discoveries of merging black holes and neutron stars have confirmed Einstein's predictions about the nature of space-time while revealing populations of compact objects that were previously undetectable. These cosmic collisions produce distinctive chirp signals as the orbiting objects spiral closer together, losing energy to gravitational radiation until they merge in a final burst of space-time distortion. The precision required to detect these waves is extraordinary, measuring changes in distance smaller than 1,000th, the width of a proton across interferometer arms several kilometers long. Future gravitational wave observatories will extend this new sense across the electromagnetic spectrum, potentially detecting the gravitational wave background from the early universe and opening up entirely new areas of fundamental physics. Stellar kinematics reveal the hidden mass distribution throughout the galaxy by measuring how stars move under the influence of both visible and dark matter. The rotation curves of spiral galaxies provided some of the first evidence for dark matter, showing that stars in the outer regions move too quickly to be held in orbit by the gravity of visible matter alone. More detailed studies of stellar motions in the Milky Way have mapped the three-dimensional structure of our galaxy's dark matter halo, while also revealing evidence for past merger events preserved in the phase space distribution of stellar populations. These kinematic studies complement direct dark matter detection experiments by constraining the properties and distribution of dark matter particles on galactic scales. The precision astrometry provided by space missions like Gaia has revolutionized this field by measuring the positions and motions of billions of stars with unprecedented accuracy. Cosmic ray acceleration occurs at some of the most energetic sites in the universe, including supernova remnants, active galactic nuclei, and gamma-ray bursts, yet the detailed mechanisms remain partially mysterious. These high-energy particles, primarily protons and atomic nuclei, can achieve energies millions of times greater than what human-built accelerators can produce, suggesting the operation of natural processes that efficiently convert the kinetic energy of shock waves and magnetic reconnection events into particle acceleration. The highest energy cosmic rays, with energies exceeding 10 to the 20 electron volts, pose particular puzzles, since they should interact with cosmic microwave background photons and lose energy before traveling far from their sources. Understanding cosmic ray acceleration, narration is crucial for explaining the high-energy phenomena observed throughout the universe and for predicting the radiation environment that future interstellar missions will encounter. The interplanetary dust cloud that fills our solar system creates the zodiacal light visible before dawn and after sunset as a faint, triangular glow extending along the ecliptic. This material, consisting of tiny particles shed by comets and collisions between asteroids, spirals slowly inward toward the sun under the influence of radiation pressure and gravitational perturbations. The dust particles range in size from nanometers to millimeters, with the largest ones creating visible meteor showers when Earth passes through their orbital paths. Studies of interplanetary dust provide insights into the composition and evolution of small bodies throughout the solar system, while also revealing how material is transported and processed in planetary systems. The dust cloud represents a dynamic system, stem in which material is constantly being added by comets and asteroids while being removed by solar radiation pressure and planetary perturbations. Exoplanet atmospheres tell stories of worlds shaped by forces we can barely imagine. Some planets orbit so close to their stars that their dayside temperatures reach thousands of degrees, hot enough to vaporize metals like titanium and iron, which then condense into clouds on the cooler night side before raining back down as liquid metal droplets. Other worlds experience such extreme tidal forces that one hemisphere remains locked in eternal day while the other stays frozen in perpetual night, creating temperature differences of hundreds of degrees across their surfaces. These atmospheric extremes demonstrate the incredible variety of conditions that can exist throughout the galaxy, each planet representing a unique experiment in atmospheric physics and chemistry. Galactic collisions unfold with a grace that defies their massive scale, as gravitational forces guide entire stellar populations through cosmic choreography that spans billions of years. When galaxies merge, individual stars rarely collide due to the vast distances between them, but their orbits become scrambled and reformed into new patterns that reflect the combined gravitational influence of both systems. Computer simulations reveal how these galactic dances can trigger bursts of star formation as gas clouds collide and compress, lighting up the merged system with the blue glow of newly formed stars. The process transforms spiral galaxies into elliptical ones, creating some of the largest and most massive galaxies in the universe. Through this patient accumulation of smaller systems over our cosmic time, stellar associations represent loose groups of young stars that form together from the same molecular cloud, but lack the gravitational binding to remain permanently clustered. These stellar siblings gradually drift apart over millions of years as they orbit the galaxy, their common origin revealed only through careful analysis of their similar ages, chemical compositions, and motions through space. Some associations, like the Ursa Major moving group, have spread across large portions of the sky, yet still retain enough coherent motion to betray their shared birth. The study of these dispersing groups provides insights into the star formation process and helps astronomers understand how molecular clouds fragment to produce multiple stellar systems simultaneously. Circumplanetary disks around forming gas giants serve as miniature versions of the protoplanetary disks that surround young stars, creating the conditions necessary for moon formation around Jupiter and Saturn. These disks of gas and dust, fed by material accreting onto the central planet, provide the raw materials from which regular satellite systems can form through processes similar to planetary formation, but on a smaller scale. The regular spacing and nearly circular orbits of Jupiter's 4 largest moons reflect their formation within such a disk, while the irregular outer satellites likely represent captured asteroids or comets that were trapped by the giant planet's growing gravitational influence. Understanding circumplanetary disk evolution helps explain why some gas giants have extensive moon systems while others have only small, irregular satellites. Solar system debris tells the story of our cosmic neighborhood's violent early history through meteorites that have preserved samples of the original building materials from which the planets formed. These space rocks, ranging from primitive carbonaceous chondrites to differentiated iron meteorites, provide direct samples of processes that occurred over 4.5 billion years ago, when the solar system was still a chaotic disk of gas, dust, and planetesimals. Some meteorites contain pre-solar grains that formed around other stars before being incorporated into our solar system, while others show evidence of shock heating and melting from high-velocity impacts between early planetary bodies. The study of meteorites has revealed the timeline of solar system formation and the conditions that existed during the first few million years of planetary assembly. Coronal holes in the sun's outer atmosphere create fast-moving streams of solar wind that race through the solar system at twice the normal speed, creating space weather disturbances when they encounter planetary magnetospheres. These regions, where magnetic field lines open into space rather than looping back to the solar surface, appear as dark areas in ultraviolet and X-ray images of the sun's corona. The high-speed wind streams from coronal holes can persist for months, creating recurring geomagnetic storms on Earth as our planet's orbit carries it in and out of these solar wind streams. Understanding coronal holes is crucial for predicting space weather and protecting sensitive technology from the enhanced radiation and magnetic disturbances they create throughout the solar system. Galactic chemical evolution proceeds through the gradual enrichment of the interstellar medium, with heavy elements produced by successive generations of stars, creating a cosmic recycling system that has been operating for over 10 billion years. The first stars contained only hydrogen and helium, but their explosive deaths scattered newly forged elements like carbon, oxygen, and iron throughout space, where they became incorporated into later generations of stars and planetary systems. This process continues today, with different types of stars contributing different elements to the galactic inventory, from the carbon and oxygen produced by intermediate mass stars to the iron peak elements created in Type Ia supernovae. The chemical composition of stars serves as a fossil record of this enrichment process, allowing astronomers to trace the buildup of heavy elements throughout cosmic history. Planetary migration through protoplanetary disks can dramatically alter the architecture of forming planetary systems, moving worlds from their birth locations to entirely different orbital zones. Gas giant planets can spiral inward due to gravitational interactions with the surrounding disk material, potentially destroying inner-terrestrial planets or forcing them into highly elliptical orbits. Alternatively, interactions between multiple giant planets can scatter them outward or even eject them from the system entirely, creating the population of rogue planets that wander through interstellar space. The discovery of hot Jupiters orbiting extremely close to their stars provided the first evidence for large-scale planetary migration, revolutionizing our understanding of how planetary systems form and evolve. Magnetic reconnection events throughout the solar system demonstrate how magnetic field lines can break and reconnect to release enormous amounts of stored magnetic energy in sudden explosive bursts. This process occurs in Earth's magnetotail during geomagnetic substorms, in the solar corona during flares, and in the magnetospheres of other planets when they interact with the solar wind. The reconnection process converts magnetic energy into kinetic energy of charged particles, accelerating them to high speeds and creating some of the most dynamic phenomena in space physics. Understanding magnetic reconnection is crucial for predicting space weather events and for designing magnetic confinement systems for fusion energy research on Earth. Galactic winds driven by massive star formation and supernova explosions can strip gas from galaxies and enrich the intergalactic medium with heavy elements produced by stellar nucleosynthesis. These large-scale outflows, observed in both nearby star-bursting galaxies and distant systems seen at earlier cosmic epochs, represent a form of galactic feedback that can regulate star formation by removing the raw materials needed to form new stars. The winds can carry material to distances of hundreds of thousands of light years from their host galaxies, creating vast bubbles of hot, metal-enriched gas in the intergalactic medium. This process helps explain why smaller galaxies tend to have lower metallicities than larger ones, as their weaker gravitational fields are less able to retain gas heated by stellar feedback. Trojan asteroids demonstrate the subtle but important role of gravitational resonances in shaping the architecture of planetary systems, with these objects trapped at stable Lagrange points that lead and follow planets in their orbits around the Sun. The dynamics of these resonant relationships reveal how small gravitational perturbations can accumulate over millions of orbital periods to create stable or unstable configurations, explaining both the persistence of certain asteroid populations and the gaps in others. Jupiter's Trojan asteroids provide natural laboratories for studying celestial mechanics and serve as pristine samples of early solar system materials that have been protected from major collisions by their stable orbital configurations. Similar Trojan populations around other planets and even some exoplanetary systems suggest that these resonant relationships are fundamental features of gravitational systems throughout the universe. Stellar winds create vast stellar bubbles in the interstellar medium as they sweep up surrounding gas and dust, carving out cavities that can persist for millions of years after the originating star has ended its life. These wind-blown bubbles, energized by the continuous outflow of charged particle from stellar surfaces, can trigger star formation in their compressed shells, while simultaneously clearing large volumes of space around massive stars. Wolf-Rayet stars and other evolved massive stars create particularly impressive bubbles through their intense stellar winds, which can reach speeds of thousands of kilometers per second and carry away significant fractions of the star's mass over its lifetime. The interaction between multiple stellar winds and young star clusters can create superbubbles that break out of the galactic disk entirely, allowing hot gas to escape into the galactic halo. Planetary ring systems exhibit complex dynamics that arise from the gravitational interactions between countless individual particles, creating structures that range from sharp-edged gaps to broad, diffuse regions with intricate spiral density waves. These gravitational traffic jams propagate through the ring material like ripples on a pond, creating temporary enhancements and depletions that can persist for years or decades before being disrupted by other perturbations. Shepherd moons play crucial roles in maintaining ring structure by gravitationally confining particles to narrow bands, while resonances with larger moons create gaps where particles cannot maintain stable orbits. The study of ring dynamics has provided insights into many body gravitational systems and has helped astronomers understand how disk-like structures form and evolve throughout the universe. Circumstellar shells around evolved stars create some of the most beautiful and complex structures in the galaxy as dying stars gently expel their outer layers in symmetrical patterns, shaped by magnetic fields, rotation, and binary companions. These planetary nebulae, despite their misleading name, represent the final exhalations of sun-like stars as they transition from red giants to white dwarfs, dwarf remnants, enriching the interstellar medium with carbon, nitrogen, and other elements forged during their lifetimes. The intricate shapes of these nebulae, from simple spherical shells to elaborate bipolar structures with jets and knots, reflect the complex interplay of stellar winds, magnetic fields, and gravitational interactions that operate during the final stages of stellar evolution. Cosmic web filaments channel matter across vast distances through the universe's largest gravitational structures, creating highways for galaxy formation that connect dense nodes separated by hundreds of millions of light years. These dark matter scaffolds, invisible except through their gravitational effects on visible matter, guide the flow of gas and galaxies along preferred directions, creating the foam-like structure observed in large-scale surveys of galaxy distributions. The filaments themselves are dynamic structures that evolve over cosmic time as smaller ones merge to form larger networks, gradually building up the massive galaxy clusters that mark the intersections of multiple filaments. Understanding this cosmic web architecture is crucial for explaining how galaxies acquire air gas and how the large-scale structure of the universe developed from tiny quantum fluctuations in the early universe. Protostellar jets extend for light years from forming stars, creating spectacular displays of shock-heated gas that trace the complex interplay between accretion disks, magnetic fields, and stellar winds during the earliest stages of stellar birth. These highly collimated outflows, moving at hundreds of kilometers per second, carry away excess angular momentum from the forming star, while also clearing cavities in the surrounding molecular cloud that allow stellar radiation to escape. The jets often show remarkable symmetry and persistence, maintaining their narrow focus over distances that dwarf the size of our entire solar system, demonstrating the power of magnetic fields to channel and direct the flow of ionized gas across vast scales. Studying these jets provides crucial insights into the star formation process and the mechanisms that regulate stellar mass assembly. Variable star populations serve as cosmic lighthouses, whose changing brightness patterns provide fundamental measurements of distances, ages, and physical conditions throughout the universe. Cepheid variables, with their precise period luminosity relationships, enabled Edwin Hubble to measure the distances to nearby galaxies and discover the expansion of the universe, while RR Lyrae stars serve as standard candles for mapping the structure and age of our galaxy's stellar halo. These pulsating stars undergo regular cycles of expansion and contraction, driven by opacity changes in their outer layers, creating natural laboratories for studying stellar structure and evolution. The study of variable stars has revealed the three-dimensional architecture of our galaxy and provided crucial rungs in the cosmic distance ladder that extends our measurements across billions of light years. Exomoons around distant planets represent one of the next frontiers in planetary science, with indirect detection methods beginning to reveal hints of satellite systems around gas giant exoplanets that could potentially harbor conditions suitable for life. These moons, if they exist in abundance around exoplanets, could dramatically increase the number of potentially habitable worlds in the galaxy by providing stable environments with tidal heating, magnetic protection, and complex orbital dynamics that could drive atmospheric and geological activity. The search for exomoons requires extraordinary precision in measuring the tiny perturbations they create in planetary transit signals and radial velocity measurements, pushing current observational techniques to their limits while pointing toward future space missions specifically designed to detect these distant satellites. Helioseismology reveals the sun's internal structure through the analysis of acoustic waves that propagate through its interior, creating a kind of ultrasound imaging for our nearest star. These solar oscillations, with periods ranging from minutes to hours, are generated by convective motions in the sun's outer layers and travel through different regions of the solar interior, before returning to the surface, where they can be detected through precise measurements of surface velocities and brightness variations. The study of these solar sound waves has revealed the sun's internal rotation profile, confirmed the existence of the solar dynamo that generates magnetic fields, and provided precise measurements of the depth of the convection zone and the helium abundance in the solar core. Galactic bulges represent the ancient hearts of spiral galaxies, containing some of the oldest stars in the galactic system and preserving records of the violent early epochs when galaxies formed through mergers and accretion events. These central concentrations of stars, often containing supermassive black holes at their centers, show evidence of complex formation histories involving both rapid star formation episodes and the gradual accumulation of material from disrupted satellite galaxies. The chemical compositions and kinematic properties of bulge stars provide archaeological evidence for understanding how galaxies assembled their central masses during the first few billion years of cosmic evolution, when the universe was denser and galaxy interactions were more frequent than today. Cosmic dust grains, though individually microscopic, collectively play crucial roles in galactic evolution by facilitating the formation of molecules in interstellar space, absorbing and re-radiating starlight across different wavelengths, and serving as condensation nuclei for the formation of larger solid bodies. These tiny particles, forged in stellar atmospheres and supernova explosions, contain a rich inventory of heavy elements that they transport throughout galaxies and into new star-forming regions, where they become incorporated into planets and potentially life itself. The study of cosmic dust through its effects on starlight and its thermal emission at infrared wavelengths has revealed the hidden architecture of star formation in dusty molecular clouds and provided insights into the chemical evolution of galaxies over cosmic time. Binary star evolution creates some of the most dramatic phenomena in the universe when the two components interact through mass transfer, common envelope evolution, or eventual stellar mergers that can produce exotic objects like type I supernovae, neutron star binaries, and stellar mass black holes. These close stellar partnerships undergo complex evolutionary sequences as the more massive star evolves first, potentially transferring material to its companion or engulfing it entirely in a common envelope phase that dramatically alters the orbital separation and future evolution of the system. Understanding binary star evolution is crucial for explaining the observed populations of compact objects, the chemical enrichment of galaxies, and the sources of gravitational waves detected by MADI observatories. The cosmic neutrino background represents a relic from the early universe similar to the cosmic microwave background, but consisting of ghostly particles that rarely interact with matter, creating an invisible sea of neutrinos that fills all of space with a density of several hundred particles per cubic centimeter. These primordial neutrinos, produced when the universe was less than 1 second old, have been streaming freely through space since they decoupled from other forms of matter, carrying information about conditions in the very early universe that is inaccessible through any other means. While individual cosmic background neutrinos are far too low in energy to detect with current technology, their collective gravitational effects influence the formation of large-scale structure and may be detectable through precise measurements of galaxy clustering and other cosmological observables. Stellar nurseries reveal themselves through their infrared glow as dust-enshrouded regions where new stars are forming within dense molecular clouds that block visible light but allow longer wavelength radiation to escape. These cosmic maternity wards, often triggered by shock waves from nearby supernovae or collisions between molecular clouds, can produce hundreds or thousands of new stars in relatively small regions of space over periods of just a few million years. The newly formed stars gradually disperse the surrounding gas and dust through their stellar winds and radiation pressure, eventually revealing themselves as young stellar associations or open clusters that slowly drift apart as they orbit the galaxy. The study of these active star-forming regions provides crucial insights into the processes that regulate stellar birth rates and determine the initial mass distribution of newly formed stars throughout the galaxy. Planetary magnetospheres create invisible shields that protect worlds from the harsh solar wind, each one unique in its shape and strength depending on the planet's magnetic field and its interaction with charged particles streaming from the sun. These magnetic bubbles can extend for millions of kilometers into space, deflecting most of the dangerous radiation while allowing some particles to spiral down toward the poles, where they create beautiful auroras. Earth's magnetosphere has protected our atmosphere for Kuiper belt objects drift in the cold outer reaches of our solar system like cosmic time capsules, preserving samples of the original materials from which the planets formed over 4 billion years ago. These icy remnants, including dwarf planets like Pluto and Eris, follow elliptical orbits that carry them far from the sun's warming influence, maintaining surface temperatures cold enough to freeze nitrogen and methane into solid crystals. Many of these objects show signs of ancient geological activity, with surface features that suggest they once had subsurface oceans or experienced periods of internal heating that created complex terrains of plains, mountains, and crater chains. The discovery of binary Kuiper belt objects, where two similar-sized bodies orbit each other in gravitational partnership, has provided insight into how these distant worlds formed and evolved insights in the quiet suburb solar system. As we drift toward the end of our gentle journey through the cosmos, let these peaceful truths settle around you like stardust. The universe unfolds its quiet mysteries with infinite patience, each star and galaxy moving through space with the same gentle rhythm that now carries you toward sleep. Rest knowing that you are part of this vast, beautiful tapestry connected to every distant light and cosmic dance we've explored tonight. Sweet dreams, fellow traveler of the stars.